Okay, welcome to MathStat 343 Probability. This is lecture number 3. So what I want to do today is this is just a general review day. Anything you want to know from previous math classes, fair game. If you want to ask questions about future math classes, I'm happy to do that, but that may not be as useful. This is a chance for you, if there's a gap that you have or something that you find confusing or that you want to know a little bit more about, happy to talk about it. One of the things I have prepared is a short little talk about the die problem that I sent you from one of my students who actually got that as a live interview question. And he was able to answer it in real time immediately and impress the people. This is one of the skills you need to have if you're going to have interviews. It's okay to ask them, can you give me a moment to just collect my thoughts? That's perfectly fine. But you want to be able to answer, and you want to be able to just show them your thought process. How would you attack this? Even if you don't get the right answer, if you can get within a ballpark, if you can show a good way of thinking about things. One great way of thinking about things is through numerical simulation, is writing a computer program. And so how many of you have never really coded before? Okay, so if you've never coded before, then that means I get to choose what you learn. Wonderful. So I use Mathematica for the most part because when I was in college, that's what we used for our physics labs. It is a very friendly program if you're doing a lot of things in pure mathematics because it has great predefined functions. It has a lot of things that you need. It has great visuals, but to some extent, it's almost like a singing horse. What's amazing is not that the horse sings well, but that it sings at all. If you want to do something for serious computations, I would not use Mathematica. Something like MATLAB would be far better. For a lot of statistics, you'd probably use R. It really doesn't matter for the stuff we're doing, which environment you use. If it's a problem that we can attack, it can be attacked with a reasonable laptop in a reasonable amount of time. And if not, it doesn't really matter what you're using. We're not going to have the computational resources to do it. So anything that you're comfortable with is absolutely fine for this class, but I really want you to leave knowing how to do some programming. So I have some handouts online on how to do Mathematica. By all means, happy to talk to you about that. If you want to do something in another environment, perfectly fine. I may not be able to help you with the actual syntax. I can help you with the pseudocode and the thought process about how you do things, but if you're doing something in an environment that I'm not comfortable with, I will not be as good on the grammar. All right. And then the other thing I want to talk about either today or it's part of technically the lecture on Friday is just sniffing out formulas. So a lot of times, it's almost the Moses coming down from Mount Sinai method of mathematics where you have these commandments from gods, and here is the formula, and we've been divinely inspired, and this is what the truth is. How do you get this? Well, wandering in the desert, praying to the Almighty, that's one way, but most of us don't really have the time for that. So can we somehow gather some data and use that data to inform ourselves on what might be the truth? And so I'll give a really fun talk on the German tank problem. Has anybody heard of the German tank problem? Okay. This is real applied mathematics, goes back to World War II, which was not surprisingly a great lab for pushing some things very quickly into active status. So a lot of operations research trying to efficiently allocate and use resources was inspired by real world problems where it matters how well we do this. And so I want to show you how you can actually sniff out formulas by gathering some data and doing some analysis. All right, so before I start talking about things, is there anything in particular people would like to see? And I'm happy to start talking about things, and then later as I'm going, if you realize that there's something you want to see, I'm happy to pivot to that. All right, so I will start with the problem that my students sent, the die problem, do you take the bet? So you have a fierce die, numbers 1 through 6, and you roll the die, and you are paid the amount of dollars that you roll. And so if you roll a 5, you get $5. You roll a 1, you get $1. Okay. How much are you willing to pay the game? So what do you think would be a reasonable, yes?
$3.50.
$3.50. Why $3.50?
Because it's the expected value.
Good, it's the expected value, it's the mean, right? So this is one of our first major concepts in probability, the average value. And it turns out there's a lot of different ways to define average. The mean is just add up all the values and divide by the number of occurrences. And so in this one, we're weighting everything equally. And so basically, if I were to do this 6 times, I would expect 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. That averages to a 3.5. So if I pay $3.5, on average, I win back $3.5. And so there's no net harm to me in playing the game. If they said you could play the game for $3, would you be willing to play? What if you can only play once and it's for $1 million? Would you still be willing to pay? I'm sorry?
Still paying $3.
So you pay now, let's say $3 million, and if you win, you get, we'll make the ante fee $1 million. But if you win, we'll pay you a little bit more. So let's make it, if you pay $3 million,
Then you get 1
3 million, 4 million, 5 million, 6 million. Yes. So the expected value is positive for you.
How much money do I have at this point?
That's not something that we should talk about in class in public. However, if you're in a situation where your assets are such that this is not an easy question, I'm happy to discuss this with you in my office hours.
So it sounds like you say, so if I roll 1, then I get $1 million.
Yes.
So my net is 0 in that case. Like
No, it costs you $3 million to play. It costs you $3 million to play. $3 million to play.
Okay.
So on average, you make $3.5 million. Sorry, you make 500. You net $500,000. You make three. It depends how you want to phrase it. You make $3.5 million, but you have a cost of, so your net profit is 500,000 on average. So a lot of this depends on what the bankruptcy rules are. What happens if you declare bankruptcy? Oops, one rule like this should be very hesitant. To do it 1,000 times, would you be willing to play 1,000 times? Yeah. I just say, we'll settle at the end of the day. Right? And in the situation like that, very comfortable doing that. So here's now the interesting twist. So now there are 2 die. So you roll the first die, and if you like the roll, you can keep it. And if you don't like it, you have to take whatever the second roll is. And now the question is, how much would you be willing to pay for this game? So before we actually analyze this, let's try to do, simple bounds. Simple bounds for the 2 die game. And recall 1 die game, you're okay paying $3.50. So one of the things that you will learn about me very quickly is I really love extreme cases. I love weak bounds, the bounds that you can give me with the simplest possible work, the simplest possible function. If I ask you for an easy function to integrate, what function will you give me? No, come on, be nice. Be nice.
1 over equals 0.
Y equals 0, right? So you might start with, let's start off with Professor Bill. Can you integrate the function f of x equals 0? Yes. And then you make it a little bit harder. Can I give you a constant? Can I give you a linear? And if you're trying to prove the fundamental theorem of calculus, well, at the end of the day, you want to check and see, can I trust the results? I can find the area under a constant function, it's a rectangle. I can find the area under a straight line, that's a triangle. So far, the fundamental theorem of calculus allows me to find the areas of rectangles and triangles. I'm not impressed. But when you find the area under a parabola, all of a sudden, now that's some real content. Okay, so can somebody give me a number where if the entry fee is this, you would definitely be willing to play this new game? $1, okay, $1. You can do better than $1. So wait, why is $1 clear? No matter what, even if I'm an idiot and I roll a 6 on the first die and say, I think I can do better. Oh, I rolled a 1. So clearly we'll play if $1. So that is the clear. And what is the value that you clearly will not play at? Okay. We'll play at 1, not at 6. So let's see if we can tighten it a little bit. Can we do better than $1 for the lower bound? Yeah, why 350?
Better.
Almost. So you have to do a little bit of thought to prove that it's better. But you can trivially prove that it's no worse.
Yeah, if you fix.
Because you can always say, my strategy is never to use the second die. So I can't do worse. So this is what I mean about just really general arguments. If do not use second roll, it's the first game. So play at 350 for sure. So we know that the value should be somewhere between 350 and $6. Do you think it's going to be more or less than 350? More. Why?
Because you have the chance to, you have one more chance to get higher than.
Good. So if our first roll is better than 350, we'll just take it. And then if it's not, then we just play the game again with the second roll. So you expect that it should be better than 350. So expect better than 350, can take first roll if it's a 4, 5, or 6. And that happens half the time. Did I make a mistake or? Okay. So you can then try to estimate. So half the time we would get the 4, 5, 6. What would the 4, 5, 6 give us half the time? All right, so does everyone agree that this is just half the time I have a 5 on average? So this is really 1/2, and then it's 1/3 of 4 plus 1/3 of 5 plus 1/3 of 6. And then half the time, what do I get? 3.5. And this is, of course, 1/6 of 1 plus 1/6 of 6. And that's 4.25. And so that's the critical question. So for $4.25, you would be willing to play the game. So what I really like about this problem is the thought process. And can we also just get some quick rough bounds? You know, the 1 and the 6 are really obvious bounds. They're unfortunately so obvious that they don't help us. But knowing that this is an improvement of the first game, essentially, we know we would probably be willing to do a little bit more than 350. All right, so I wrote some code to do this in Mathematica. How many of you have ever written code of more than 100 lines? More than 1,000 lines? In one program. I think I'm still up if it's over 10,000 lines. The longer your code is, the more important it is to have comments, especially if there's a chance that somebody other than you may be looking at it. Now, you may be trying to make yourself irreplaceable. You're the only one who can understand what you are doing. Not necessarily the best strategy. So what I like about Mathematica is it does a nice job indenting things. If parentheses, star, parentheses is comments, it's a slightly different color. This means begin, this means ends, you know, simple for loops and whatnot. And so what I'm doing here is I'm going to just create a simple program to simulate playing this game. And so what I do is get is how much money I'm getting. So I just keep track of how much I win. I choose a random number from 1 to 6. If it's greater than 3, I'm going to keep it. So I increase how much I've brought in by X. And if it's not, then what I do is I take how much I have and I add a random integer from 1 to 6. So every language has its own commands for how you grab things. And I'm just grabbing a random integer uniformly from 1 to 6. So all the numbers are equally likely. And then I just divide by how many times I've played. And then that will tell me how much I'm getting on average. Yes?
Do we know for sure that that's cut off between the rows, just between 3 and 4?
That's a really good question. So what we could do is we could see, well, what would happen if we tried something else? So let's do it 2 different ways. first, I'm going to just present what we have here, and then we'll discuss how to answer your question. So we're going to put that in reserve. And so what I did is Mathematica has a command called timing, which tells you how long it takes to run code. And that is much better than having me sit there and looking at the stopwatch. Now, are you surprised by these results? That when I run it for 100,000 takes, 0.1875 seconds, for 1 million, 1.875 seconds, for 10 million, 18.64 seconds, and then for 100 million, 182.156 seconds. Does that seem surprising to you in terms of the runtime? So what do you notice about these runtimes? I'm sorry?
For the ratio of like time, runtime, or
Yeah.
simulation per runtime. Or not, it gets more efficient.
Well,
Linear.
So this is the question of what does it look like? So what do these ratios look like to you? Approximately 10. Remember, my computer is doing other things at the time. I might be watching an episode of Star Trek. I might be compiling a LaTeX document. Especially on the smaller things, I would be a little bit less likely to trust because that could change a little bit. The longer it is, the more likely things are going to average out. But you see that the program is roughly linear in time, so that if I want to do something 10 times larger, I know roughly how long to wait. And I know, do I have a reasonable chance of having this run? You can also look at the results, 4.255, I'm sorry, 4.25225, 4.2514, 4.25019, 4.25026. Are you surprised that it got a little bit worse? Yes.
Mathematica recycle
The random numbers?
or like, yeah, so if we have, it'd be like 100, 1,000, million, we can use the initial 100 that we ran.
No, I think it will use different ones. And one way to test that, of course, is to just run the program twice. I know in C, I think you have to be very careful because it chooses a very special starting point. And one of the advantages of this is if you want to then retest something, you can. But it is absolutely something to worry about. So here, because the program is linear, I'm just doing another simple test. I know roughly how much longer. And so if I know how much runtime I have, I can just let it run longer and longer and have more and more confidence in the true value. I don't expect things to be uniformly getting better the more simulations I do. There's going to be some noise. I expect on average, I should be getting more accurate and more precise as we go deeper and deeper. But I don't expect it to be always moving in a better direction. So I really like this problem in terms of it's giving a lot of great results. These things are very consistent. In other programs where you see it taking more and more time, you can try to extrapolate, oh God, it's going quadratically, it's going exponentially, and you can realize we're in trouble. One of my favorite quotes in mathematics is due to Paul Erdős, and it concerns the friendship graph. So assume that friendship is symmetric. If I like you, you like me. If I don't like you, you don't like me. Right? These may not be reasonable assumptions, but we will assume them for the sake of this discussion. So the question is, how many people do you need to have in a room before you have at least 3 people, all of whom like each other, or at least 3 people, all of whom don't like each other? Can somebody give me a lower bound as to, I need to have at least this many people for this to have a chance? 3. Right? If you don't have at least 3 people, there's no way. It turns out you need 6 people. If I have 4 people, I could have 2 of us like each other, and we only like each other, and 2 other people who like only each other, and no one from each like. So 4, I can easily give you a configuration. I can give you a configuration with a little bit more work for 5, and it turns out no matter how I assign friendship, for 6 people, you'll always have at least 3 who like or at least 3 who don't. You can then ask, well, what if I want at least 4 who like or at least 4 who don't like? And the great quote due to Paul Erdős is, imagine, and I think he really phrased it like this, a fleet of alien warships shows up over our skies and demands to know the answer. And if they want to know the answer for 5, and they give us a year, we devote all of our resources to finding it. If they want 6, we fight. The computational complexity of solving 6 and just looking at every possible configuration is just too much. 5, we can probably do in a year. If the fate of humanity depended on it, yes. 6, too much. So you really want a sense of how hard are these problems going to be. A lot of times in class, you have these cookbook problems that are designed to be nice and simple that you're going to be able to solve. In the real world, it's not necessarily going to be like that. All right, so we've talked about the logic behind this. What I want to do now is I'm going to shift to the code. Okay, so here is the code. And so what I'm going to do now is we want to change it, right? So let's make the program a little bit better. Let's introduce cutoff as a new parameter. And then now if x is greater than cutoff, my internet connection is unstable. Okay. If x is greater than cutoff, then we'll have get equals def plus x and otherwise. So what would you like to try for your, so do you agree that your strategy is going to be, we have a cutoff, if our number is greater than the cutoff, we take it. And the only thing you're disputing is whether or not the cutoff should be 3.
Yeah, or I'm just curious.
No, and that is that is a great question. That would have been a wonderful question for them to then ask. Now we can do the calculation very easily on the theoretical side. But before doing the calculation on the theoretical side, let's just explore. What do you think might be better than 3? So do you want to go to 4 or do you want to go down to 2? So do you think it would be better to be keeping 3s?
Oh, I would be ambitious.
Well, but let's think. Could it, before we do a long computation, it's nice to just ask yourself some basic questions and see if it's worth doing. So my wife works in marketing and she often does a lot of surveys. And one of the things you learn is you never ask a question whose answer doesn't help you. What do we get on average with the second die? Would we ever want to take a 3 on the first die? So I think we can, I think we can prove that you would never take a 3 on the first die because on average we'll do better on the second die. So for my cutoff, I'm not gonna accept a 3.
Yeah.
I may not want to keep the 4.
Yeah.
Did you have a comment?
No, I was just gonna say 4.
Yeah, so let's try 4. And so that means we're only going to keep a 5 or a 6, right? Now we're not going to let all of them run. Okay, so we're earning on average 4.16. Does anybody remember? Let's see, before we were earning on average 4.25. So it goes down. Is this surprising? Well, we're throwing away whenever we get a 4 on the first die. And what are we getting on the second die? A 3.5. So if you have a 4, if you risk going to the second die, it shouldn't be able to help you. But this is the power of being able to write simple code and do some quick experiments. Is we can quickly do this now. And it's already done, I think 3 of them. And now today it's running a little bit faster, I think. But the last one was 17 versus 18. So it's a little bit faster. But about how long is 182 seconds? 3 minutes. So it's going to take it about 3 minutes to do the last one. And you see this number 4.166. Do you think this is going to be a rational number? Probably when you look at the expected value, everything in sight is an integer. And so I would expect that this is going to be a rational number when we do all the divisions and stuff at the end. And so I'll let it just keep running while we're talking. There's no reason for my computer to relax. But any questions about this? This is the level of coding I want you to be able to do. Simple for loops to just go through things. You want to be able to store things. You want to be able to display the results. You want to put it in a nice, easy way so that people can see what's going on. Here is what I earn on average. It's very easy for me to look at this and see what the answer is. If statements are extremely valuable. So I want to know for statements, if statements, while statements is another great thing to know. While this condition holds, do the following. Yes.
What's the null represent in the output of
what it just means is that I have written this as a function, and the function itself is not passing out anything when it's done. So it's just doing everything internally and printing things out. What I could do is I could return maybe the average, and that might be a good thing for it to return. Yes. Yes, because if we did inclusive, then that would be the same as having a cutoff of greater than 3. So they would be equivalent. And so a lot of times there is more than one way of writing things. And depending on how you choose to write it, it will look a little bit different, but it will actually be the same. All right. Any other questions on this? All right, so we almost talked long enough for it to finish. All right. Is there any general material you want to go over? Anything from integration, anything from Math 150, 151, or anything from linear algebra? Yes. Integration. Let's do some integration. Yes. So I know at least one person here has heard me talk about this subject before. What is your least favorite method of integration? And if you don't answer what I'm thinking of, it's not because you like it, it's that you have been so traumatized by it, you've forgotten it. And as soon as I say, oh yes, I really hated that. So what is, I'm sorry, what is your least favorite integration method? If you want, I'll tell you. Partial fractions. How many of you remember partial fractions? How many of you never did partial fractions? Okay. I mean, it could be you were just so traumatized, you lost the memory. It's possible. All right, so let's talk about integration methods. So the first year I was at Williams, my daughter was born in the spring when I was teaching differential equations. And I taught differential equations as a father who is experiencing yet again, what is it like to have a newborn baby? And the baby is crying. So what do you do when the baby cries? Okay, one possibility is get it food. What else? Pacifier. What else? Hold it. Make funny faces. Change the diaper. When you have a baby, you will realize that goes a little bit higher on the list than you might be putting right now. But there's a bunch of things you can try. So how many of you are kicking yourself that you didn't answer the phone? Professor Miller, why don't you just ask the baby what she wants? Well, why don't you do that? Babies can't talk. Or at least they can't talk in a way that we can understand initially. But after a while, you start to realize that's the I'm hungry cry. That's the I want to be held cry. When I defended my PhD thesis, there were 2 non-mathematicians in the room, my wife and one of the deans, because I was involved in residence life stuff at Princeton. And afterwards, my wife goes, that's your extremely nervous voice. That's the voice you used when you were asking me out. And so after a while, you start to pick up on little signals. When you're integrating, there's a bunch of different things you can try. So have a list of methods. Try something. If it works, wonderful. If it doesn't, go on to the next. And so there's a lot of things in mathematics where you just have a bunch of techniques and you just try them one after the other after the other. And so for integration, we have change a variable, which is often called, I think, U substitution. Related to that, we have trig substitution, which is a special case. We have integration by parts, which is really the product rule. We have partial fractions. And use some more advanced techniques. Just, converting to a double integral. And then there is differentiating under the integral sign. So the more techniques you know, the more likely you are to have success. Richard Feynman, Nobel laureate in physics, had a reputation for being an integration master. People would come to him stuck, and he would look at the problem and go, "Here you go." And they were amazed at how quickly he did it. And the reason is, he said, "Well, look, I'm at Princeton or MIT. The people who are coming to me are not idiots. If you could have handled it with one of the standard methods, they would have found it. So I'm going to assume they've tried all the standard stuff and they've all failed. I'm going to go straight to differentiating under the integral sign." And he would solve it that way. The other one, which I know I put in the book, is the bring it over method. Okay, so let's talk about, say, integration by parts. So if I give you f of x, g of x prime, that's f prime of x, g of x, plus f of x, g prime of x. So this is the product rule. So what we do is we actually write this now as, u of x, v of x prime is u prime of x, v of x, plus u of x, v prime of x. Or, the integral from a to b of u dv. So by u dv, I mean u of x, v prime of x dx. And think of it as dv dx dx. So when we write u dv, what we really mean is v prime dx. This is the shorthand notation that I calculus books use. Is this what people are used to seeing, u dv? So then this would be equal to the integral from a to b of u. This would be u of x, v of x at a, b, minus the integral from a, b of v prime of x, I'm sorry, v du. And what we're really doing is we're just taking the line above and we have the u prime, v prime. So if I integrate this, that's the same as the integral of this minus the integral of this. Well, what's the integral of the derivative of uv? The integral of the derivative of uv is just uv. So the easiest function to integrate is a function that is given to you as a derivative of something else. Now, when you integrate, it's only up to an arbitrary constant. But since I'm integrating from a to b, the arbitrary constant is going to cancel out because we're subtracting. And so this is integration by parts. So if I give you, for example, say I want the integral from 0 to pi of x cosine x dx. I have to decide, what do I want for u? What do I want for dv? I really like making the table like this. When you make the table, you're less likely to make a mistake. For this problem, there's really only two possibilities. I take u to be x, or I take u to be cosine x. Which do you think is better, to take u to be x or to take u to be cosine? Cosine. So if I take u to be cosine, then the derivative is going to be something involving a sine. And if I take dv to be x, then v is going to become something like x squared. So I'm going to get a higher power of x. Okay, there's two options. If option one's not working, option two, let's go with option two. Okay, so if I go with option two, the reason I can't do this integral is because I've got this x here. If I just gave you cosine, no problem. So let's try u is equal to x, dv is cosine x dx. So du is just going to be dx. And then what's the integral of cosine? It's sine. And so always draw the unit circle And so you can see in the first quadrant, the derivative of cosine is negative, but the area under cosine is going to be positive. Well, a better way of doing it is here. What's the derivative of cosine x? Negative sine of x. And so the way I like to remember this is minus sine. All right, that's how I like to remember. Where does the minus sign go with? The derivative of cosine is minus sine. And when you look at this, you can see as the angle increases, cosine is decreasing. All right, so now I just put pieces together. So my integral is going to be uv at 0 pi minus the integral from 0 to pi of v du. And so I am not rushing. I am showing every step. The more steps you show, the less likely you are to make a mistake and skip something. Now I'll substitute. So uv is going to be x sine of x at 0 and pi minus the integral from 0 to pi of v du. So it's going to be sine of x dx. Okay, when I look at x sine of pi, what is that at 0 and pi? That's just 0. Okay, not bad. And then the other one, what function has derivative sine? Negative cosine. Ah, good. So the negative is going to reinforce with the negative. I'm going to get plus cosine of x at 0 and pi. What does that equal? Negative 2. Does that seem reasonable? Who thinks that this answer is reasonable? So here is 0, pi halves, pi. Cosine starts off at 1, and it comes down like this, right? But we have the function x as well. And so the function x coming up like this. So notice that the negative region is hit with a larger value of x than the positive region is. Negative region gets a larger weight. We expect negative answer. So again, whenever you're doing these calculations, it's wonderful if you can just quickly look and see, what do I expect the answer to be? And looking at this problem, if I just integrated cosine of x, I would expect to get 0. The positive parts of cosine are weighted by less than the negative parts of cosine. So I expect the answer to be negative. Can anybody give me a bound for this integral? So we know it's negative. So 0 is greater than or equal to the integral from 0 to pi of x cosine x dx. How negative could it be? Why negative pi? You're close. So one is it's definitely negative pi squared because the interval has length pi. And so the worst case is when cosine is always negative 1. And so you're clearly, because you have the positive stuff. And so, if we just integrate from pi halves to pi, that will be a lower bound because the positive stuff is going to bring it up. So we could actually improve to greater than or equal to -1/2 pi squared. Right? And so now, pi squared is roughly 10, so this is roughly -5. It's a bit high, but you could do a little bit better. You could maybe estimate a little bit what's going on in positive stuff, but I don't want to go into too much detail, but it's nice to have some ballpark answer. Yes.
Could you do pi over t squared, negative pi, negative times pi over t squared? Because that the left half you get, but pi.
Oh, because you have some contribution from the first part?
Yeah.
The problem is you have to use, you need a lower bound for the positive part. And the problem is the lower bound is if you use x equals 0, that just gives you 0. And what you could do is you could, well, unfortunately, cosine is largest near 0 and x is largest near pi halves. You could look maybe from the interval pi fourths -1/8 to pi fourths +1/8 and do something like that. So there are games you could do to try to estimate this. And then that would lead to improvements. And we'll see stuff like that later when we look at factorials. So as an aside, we didn't get to this last time. Can somebody tell me what 5 choose 3 means? What does this mean? Yes.
The number of ways to order, to choose 3 people from 5, the order doesn't matter.
Good. 3. Three from 5 when order does not matter. And what is this equal? So it's 5 times 4 times 3 factorial over 3 factorial times 2 times 1. The 3 factorials cancel, and so this is going to just be 10. So 3 choose 5 would be 3 factorial over 5 factorial negative 2 factorial. What should this equal? It should be 0, right? How many ways are there to choose 5 people from 3? Even the greatest magician cannot choose 5 people from 3. So what does 3 factorial equals? 3 factorial is 5 factorial. Thus 0, I'm sorry. It should be negative 2 factorial. Thus negative 2 factorial is, what should it be? What must it be? You can use the extended real numbers. It should be infinite, is infinite. And it turns out we will see later in the semester what's called the gamma function. And this will be very important for us. So gamma of s is the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. Gamma of m plus 1 equals m factorial if m greater than or equal to 0 is an integer. So it's basically like a shifted factorial function. And it turns out that this new function will blow up whenever you take s to be a negative integer. And what's nice about that is it allows us to interpret the combinatorial coefficients the way we would like to. All right, so we just did integration by parts. That's one of the most useful things to do. Another one that I want to do quickly is change a variable. And I will do something related to an integral that will arise later. Let's say we want the integral from 0 to infinity of x e to the negative x squared over 2 dx. Okay. If I gave you just e to the negative x squared over 2, we don't have a nice way to integrate that. There's no nice closed form for that. But if I rewrite this as the integral from 0 to infinity of e to the negative x squared over 2 x dx, this piece over here is looking like the derivative of negative x squared over 2. So if I let u equal x squared over 2, then du is equal to x dx. And so this is actually set up to make all the constants work out very nicely. And so this is the same as integrating u goes from 0 to infinity, e to the negative u du, which is just what? It's negative e to the negative u at 0 and infinity. Well, the negative sign just flips the order of integration, and you just get 1. So let's just do one last example. We still have a little bit of time. Let's integrate from negative infinity to infinity, x e to the negative 4x squared dx. And I can write that as negative infinity to infinity, e to the negative 4x squared x dx. What do you want to take u to be? What do you want du to be? Okay, so if we do that, then when we have e to the negative 4x squared, we're going to have to take into account that. I would rather make the exponent nice and then take that into account with the du than to have the exponent bad. So 4x squared. So what's du going to be? Dx. And so what I can do is I can look at the integral x goes from minus infinity to infinity. I need an 8, so I'll put a 1/8 over here, e to the negative 4x squared, 8x dx. So what does this become? It becomes 1/8 integral u equals what to what? So I get e to the minus u du. I'm just having some fun. So what I did is I deliberately tried to trick you. Be explicit. We have x goes from minus infinity to infinity. U is 4x squared. So what does u go from? Four times negative infinity squared. What's 4 times negative? So we have u going from infinity to infinity. It's not 1-to-1. We need to do twice the integral from 0 to infinity of x e to the negative 4x squared dx. If we try to do it from negative infinity to infinity, the problem is when we change the variable, we're actually just going from infinity to infinity. You have to be very careful that there has to be one value of your input to one value of the output. It's got to be 1-to-1 onto. So, a function like this that's increasing, this is okay. A function like this is not, because if I give you a value of y, which of the two values of x do I go to? There's two choices. Whereas over here, if I give you a value of y, there's only one choice of x. So this was meant to be deliberately tricky. I deliberately was trying to get you to say the wrong thing. You're more likely to remember things like that. I will end, because we have half a minute, with the following algebra test. What's 16 over 64 in lowest terms? All right, 19 over 95. Come on, come on. 1/5. 49 over 98. 12 over 24. Wait, I get 1/4. 16 over 64 cancel the 6s, it's 1/4, 19 over 95, cancel the 9s, it's 1/5, 49 over 98, cancel the 9s, it's 4/8. So clearly, the way you divide two fractions when the opposite of the main diagonal is equal is you just remove it. We had 3 data points. So cases must be exhaustive. So build intuition, but be careful. Just because something works for a while does not mean it's always going to work. All right, this is a good time to stop.